Yeah, go ahead, sir.
Hello students, welcome to this live lesson 2 on this topic of approximate methods in quantum chemistry. I am Sabyashachi Mishra. I hope in last 8 weeks you have enjoyed taking this course. We have kind of covered the entire syllabus that we promised. In the previous live session, in next 2-3 minutes before I start getting your questions, I would try to summarize what we have done in this course. We had one live session a month ago, which was after completion of 4 weeks of the course. In that, we mostly focused on the overview of quantum mechanics, in which we talked about the principles and postulates of quantum mechanics, the language that one uses to describe a quantum mechanical system. And in addition, we also looked at some exactly solvable models. So that actually prepared us the groundwork for the next part of the course. The main aspect of this course is looking at the approximate methods. So the first approximate method that we discussed was the variational principle, variational theorem, its examples. We also took it to linear variational method. And once we learned about the linear variational method, we could easily take it to chemical bonding, either by valence bond theory or molecular orbital theory. So in those parts, you saw that how the very helpful, very famous valence bond theory and molecular orbital theory, for example, are mere outcomes or mere applications of this variation, a linear variational principle. While variational principle was quite helpful, but it also had several shortcomings, in particular its applicability only to mostly to the ground state, as well as the requirement to make a Gauss function. With these weaknesses, we looked at another approximate method, and that was the perturbation theory. And while discussing the perturbation theory, we derived the expressions for first order, second order wave function and energy correction, and then we looked at how we can apply perturbation theory. In particular, for example, we talked about the Zeeman effect, the effect of external magnetic field, the spin-orbit coupling, and also we discussed at great length the molecular response to electric field. And all this perturbation theory we looked at for the non-degenerate states, but we also discussed the helium atoms excited states using degenerate perturbation theory, because if you recall our discussion on perturbation theory, the standard perturbation theory for the non-degenerate state could not be applied to degenerate systems. So that was the topic of the first live session at the first half of the course. And in the second half of the course, which will be the focus of this particular live session, in this half we discussed about many electron systems. So like first few classes we spent as to the basic language, the basic necessities to describe a many electronic system. For example, how can we write the wave function of the many electronic system? What are the necessary conditions that the wave function must fulfill when the wave function represents a many electronic system? So for example, we talked about the spin orbitals, we looked at Slater determinantal wave function. That means the wave functions are now expressed in terms of Slater determinant. In standard quantum mechanics, you know how you can evaluate expectation value, how you can evaluate properties. But when the wave function is described by a Slater determinant, in that case, how do you calculate the integrals? How do you get the expectation values? We learned them from the super-Condon Slater rules. Once we got some experience as to how we can deal with Slater determinants, various properties of it we discussed, then we introduced the self-consistent field method, where we said that, okay, this is yet another approximate method to solve many electron problems, because we discussed again and again that when we have more than one electron, the electron-electron correlation makes it very difficult for us to solve this problem exactly by quantum mechanics. So therefore, this electron-electron correlation, instead of solving it exactly, what we try to do is that we said that, okay, we'll look at one electron at a time, and then rest n-1 electron of the system will be described by a potential. So there, and then we changed from this electron to the next electron, and this way we went around for each and every electron. So therefore, what we did is that instead of solving an n electron problem in one go, we solved n number of one electron problems, but then that became somewhat easier for us to do. And this procedure goes by the name self-consistent field method. We solved this iteratively. We learned how this idea that how we can define an effective potential that an electron experiences because of other electrons and the nuclei, how we can express this idea into a variational calculation. So we used the functional variational method for this, and then we derived our equations and we looked at the Fock operator. We talked about the non-canonical Hartree-Fock equation, and we again try to convert it to canonical Hartree-Fock equations. But both canonical or non-canonical Hartree-Fock equations, they were integral differential equations. While one can solve them, but then they are not very adaptable to computational uses. So in that case, we introduced the wonderful idea of Ruthan to introduce the basis set. And once we introduced the basis set, we quickly converted the Hartree-Fock equations to Hartree-Fock-Ruthan equations, where we looked at the solution of Hartree-Fock Ruthan equation became an iterative solution of the Fock matrix. So we defined the density matrix, which are the coefficients of the basis set. We defined the Fock matrices, and we see that how we can iteratively solve the Fock matrix by making an initial guess of the density matrix and iteratively solve Fock matrix until the energy converges. At the end of our Hartree-Fock calculation, when we have the Slater determinant, how we can use them to get the properties. Now, so far in this course, we looked at different methods to obtain energies, to obtain wave functions. And of course, once you have the wave function, you can evaluate different properties. But one particular approximate method, we took it at the end of the course, it was in the last week of the course, was the time-dependent perturbation theory. While all other methods were very important for electronic structure, bonding, reactivity, when it comes to spectroscopy, the time-dependent perturbation theory is very essential. In that context, we first looked at the time-independent Hamiltonian, because we know that most of our molecular Hamiltonian are time-independent Hamiltonian. That means the potential energy doesn't have explicit time dependence. In such cases, we could express the station. We learned how to write down the stationary state, how to write the corresponding, which are the non-stationary states. So after looking at the time independent systems, we also said, okay, what if the potential energy has explicit time dependence? In such cases, we started looking at the time-dependent perturbation theory. First, we looked at the two-state problem, the famous Rabi's formula, where we said that okay, the time evolution of an initial empty state depends on the strength of the coupling, that means the perturbation, as well as the energy difference between the two states. So Rabi's formula was extremely useful in understanding the time evolution of a two-state problem. But we also took it forward, and we took it generalized to n number of electronic states, and we looked at several different forms of perturbations. For example, we talked about constant perturbations, that although it is time-dependent perturbation, but this during the application of the perturbation, this perturbation value remains constant. Or we also looked at a slowly switched constant perturbation. And finally, we looked at the most important perturbation is that was the oscillating perturbation. I call it most important because that has enormous significance to spectroscopy. This oscillating perturbation, time-dependent perturbation, simply represents the case where the light interacts with, or the electromagnetic radiation interacts with matter. While discussing this, we also come across this very useful form is golden rule, which helps us getting an estimation of the spectral intensity from molecular level information. and we also talked about the Einstein coefficient, where we talked about the induced and spontaneous emission processes, and then we learned how different Einstein coefficients are related to each other, and so on. So this is the overall summary of the course that we have had. And if you have any more questions, you please start asking as we progress in the course. Then we'll take up those questions and do this. Okay. All right. So while we are waiting for your other questions, we could discuss a few problems. Based over last several weeks, you people have been asking us several questions in the discussion forum, and I see that you have got several doubts on many different things. From that, what I understood is that where the majority of the people are facing problems, to help along that direction, I have selected a few questions from the assignments. We can do a quick discussion of them, and I keep monitoring. If we get any more live questions, we'll take them up as and when they come. All right. So one problem that we should be able to address after taking this course is that given an electronic configuration, because from very beginning, from high school level, we are able to write down the electronic configuration of an atom, and once we know about the molecular orbital theory, we start writing down the electronic configuration of a molecule by filling electrons in different orbitals. But in this course, we learned that when we have electrons occupying certain orbitals, what contribution do these electrons make to the overall energy? For example, given if we have this kind of electronic configuration where there are two molecular orbitals, orbital 1 which is doubly occupied and orbital 2 which is singly occupied. Now each electron, when it occupies an orbital, it contributes to a core energy, and it also interacts with the other electrons, thereby, and we know that the other electrons, the electron-electron interactions can either be described by the Coulomb energy J or the exchange energy K. But each electron, when it occupies an orbital, it contributes the so-called core energy or one electron energy, which corresponds to its kinetic energy and its potential energy with other nuclei. For example, since we have two electrons in orbital 1, so therefore we have got 2 times H11. H11 is the core energy corresponding to the orbital 1. Whenever an electron occupies orbital 1, that core energy becomes H11, and since there are 2 such electrons, so therefore 2H11, and 1 electron in second orbital, so therefore the core energy corresponding to that is H22, and we have J11 because we see that there are 2 electrons in the same orbital, molecular orbital 1, and these 2 electrons can have Coulomb interaction between them. But we know that the 2 electrons, when they occupy the same spatial orbitals, they must have different spin. So therefore they cannot have exchange interaction, because exchange interaction happens only between 2 electrons of same spin. We derived this in our class. So this is why we have, and then the J12 is the Coulomb energy between electron occupying an orbital, electron in orbital 1 and electron in orbital 2. So 2 such Coulomb interactions you can imagine, and then we have finally the exchange term, exchange integral between 1 and 2, because you see that this electron and this electron in orbital 1 and orbital 2 have got the same spin. So therefore they contribute to the exchange interaction. All right. Fine. We now look at another problem, which says that I am expressing two Slater determinants, psi1 and psi2. You can see this Slater determinants normalization constant is 1/6, which is factorial of 3. That's because I have got 3. This is a Slater determinant of 3/3 dimension. So we have psi1 and psi2. And the question is, what is the internal product between psi1 and psi2? One possible misunderstanding the students would have, they would immediately see, they say that, okay, these two are different Slater determinants, because here I see chi A, chi B, chi C, and here I see chi C, chi B, chi A, and we know that the Slater determinants are orthonormal, so therefore, since they are different, they might be 0. But then when you look at these two Slater determinants closely, you will see that they differ by a simple interchange. So if I exchange electron 1 and electron 3, so that means chi A and chi C, you will see that I will go from psi1 to psi2. So therefore, we know that when I exchange two electrons, the Slater determinant becomes negative. So therefore, psi1 and psi2 are related to each other. In fact, they are negative of each other. If psi1 and psi2 were equal to each other, then we know that since they are all normalized, so therefore their internal product would have been +1. But since they are negative of each other, so therefore their internal product is going to be -1. We look at another problem here. So it says that what the interelectronic repulsion, we have a many-electronic atom. The interelectronic repulsion can lift which kind of degeneracy? The degeneracy of which quantum number? Is it the principal, or the azimuthal, or the magnetic, or all of this? The question relates to the situation where we have to compare, let's say, the hydrogen-like system, which is essentially one electronic system, there is only one electron, to any other many electronic system. We saw when we looked at hydrogen atom problem, we know that the energy depends only on principal quantum number. L and M values, they are all degenerate. So in hydrogen atom, 1s has one energy, 2s and 2p orbitals have same energy, 3s, 3p, 3d have same energy, 4s, 4p, 4d, 4f have same energy. So that means when I'm talking about 2s and 2p orbitals, they have same energy. That means the energy levels do not distinguish between different L values have the same energy. But when I come to many electronic system, because of interelectronic interaction, electron-electron interaction, this degeneracy of 2s and 2p orbitals gets lifted. So for example, in helium atom, we have seen that 2s and 2p orbitals should have different energy, but that is happening because of the electron-electron interaction. We discussed that the contribution can be from the Coulomb terms or can be from exchange term, and so the L is a possible answer. What about M? The magnetic quantum number doesn't. The name actually suggests that we can actually lift the degeneracies of this magnetic quantum number only by applying magnetic field. So that means 2px, 2py, 2pz. Even when there is electron-electron repulsion, these 2px, 2py, 2pz orbitals should still have the same energy. And we discussed that when we were looking at the excited state of helium atoms. All right. We had a few questions on this particular problem. This particular problem tests your knowledge about how you can interpret the Hartree-Fock calculations. So this is done for a hydrogen atom, so hydrogen molecule, forgive me. So it says that when you do an SCF calculation for the hydrogen molecule, it gives rise to two molecular orbitals, the bonding sigma g and the anti-bonding sigma u. This we know. But the problem also tells that the orbital energies of the bonding orbital is minus 0.62 atomic unit, and for the anti-bonding it is plus 0.40 atomic unit. So these are the orbital energy. On top of it, the problem also gives that the 2 electron integrals over these molecular orbitals are here. So what are these 2 electron integrals? So you can see that the first line, it simply indicates that when the this is the 2 electron integral where the pra and the ket are same, so both the electrons occupy the bonding orbital. The second line says when the 1 electron in sigma g, another in second electron is in sigma u, and so on. Now, question that it asks is this: what is the SCF electronic energy of hydrogen? So that means what is the Hartree-Fock energy of hydrogen given the information. One mistake that students often do is that they say that, okay, we know that in hydrogen ground state there are 2 electrons in the sigma g, that is the lowest energy configuration, and since we know that the orbital energy of sigma g orbital is minus 0.62, and therefore since there are 2 electrons which are present in the sigma g orbital, so maybe the energy is twice this orbital energy. But that is wrong, because we discussed at a great length in our lecture that the orbital energy and Hartree-Fock energy, we must pay attention to the differences between the two. The orbital energy is the expectation value of the Fock operator when the system is defined by that particular spin orbital, whereas the Hartree-Fock energy or the SCF electronic energy is obtained when I make the expectation value with respect to the total Hamiltonian, molecular Hamiltonian, when the state is defined by the Hartree-Fock wave function or the Hartree-Fock Slater determinant. We know that how we, given the spin orbitals, how we can define the Hartree-Fock Slater determinants. We simply occupy the lowest n number of spin orbitals by electrons, and that Slater determinant defines the state. So that particular expectation value will give me the Hartree-Fock energy. So the sum of the orbital energy is not the Hartree-Fock energy that we have. Rather, there is a somewhat nuanced difference. For example, the orbital energy, call it epsilon 1, of course it has this relation, we derive this, that is the core energy plus the Coulomb energy J11, whereas the total electronic energy is twice H11 plus J11. So you see, if you multiply simply 2 into this orbital energy, you would overcount this J11. So since you see the orbital energy and the total electronic energy, so we have H11 and J11. So this J11 value is simply given here as 0.56 atomic units. So solving this, you can figure out that the total electronic energy will come out to be minus 1.80 atomic unit. So this question tries to teach you how to carefully distinguish the orbital energy from the total electronic energy. One physical significance of the orbital energy that we have, because remember, this orbital energy is coming because we have defined this special Fock operator, and these orbital energies are eigenvalues of that Fock operator, which is defined in a particular within the self-consistent field idea. So this is not one of the most natural way of constructing an operator. So therefore, this orbital energy wouldn't have wider physical application, except for the very interesting application that we discussed within Koopman's theorem, saying that the orbital energy can also be used for an estimation of the ionization potential and electron affinity. Although ionization potential is a quantity that we can faithfully obtain from the orbital energy. For the electron affinity, it is often a rough approximation, but it works within the so-called frozen orbital approximation. All right. Let us see if we have any more questions. No. All right. In that case, we continue with our discussion. the preset questions. So now the next question talks about the formation of the canonical set of orbitals from non-canonical by doing the unitary transformation. The problem tells the following. So suppose we have the set of non-canonical spin orbitals chi-A's, so they form a complete set that we obtained from the Hartree-Fock procedure. Now we subjected this non-canonical set of spin orbitals to a unitary transformation and obtained a set of canonical spin orbitals, that is chi-A prime. Now, given that we have the non-canonical or canonical spin orbitals, we can always construct the corresponding Slater determinants, and that's what we have done. Psi and psi prime are the Slater determinants that we have constructed from the non-canonical and canonical spin orbitals respectively. Now, the question asks which of the following are correct. For example, the first option says that the two Slater determinants that you constructed, one from the non-canonical set, another from the canonical, they are orthogonal. Now, if you recall, the reason why we are very happy with this unitary transformation is that while it preserved the orthonormality of the spin orbitals, that means chi-A's were orthonormal set of spin orbitals, the non-canonical spin orbitals, but after that unitary transformation, the new set of canonical spin orbitals chi-A prime, they also constituted a new set of orthonormal set of spin orbitals. But the wave function, the Slater determinant wave function psi and psi prime, they differ only by a phase, especially if they are complex. Otherwise, they are simply plus minus of each other. So therefore, they are not orthogonal to each other. That means internal product of psi and psi prime is not going to be 0. So they are not orthogonal. What remains orthonormal or orthogonal are the canonical spin orbitals they themselves. Now the second is the set of spin orbitals chi-A, that means the non-canonical spin orbitals, they are orthonormal set, but that is not true for chi-A prime. This is what we just discussed, that both canonical and post-unitary transformation, both non-canonical and the post-unitary transformation, the canonical spin orbitals, both are represent orthonormal set. Now the energy associated with psi, that is the non-canonical, is always less than that associated with psi prime. Now this is wrong, because we know that all properties associated with the canonical or non-canonical Slater determinants, they are going to be same, because these two wave functions, the Slater determinants, simply differ from each other by a phase. So, and since all the expectations value have a bra and a k term, so therefore the net result will be same. So the energy, whether you are in the non-canonical sense or the canonical sense, energy wouldn't change. The option D, the Fock operators constructed from the two set of spin orbitals are the same. This is true because we explicitly showed that the sum of the Coulomb operators, the sum of the exchange operators, and therefore the Fock operator was invariant to the unitary transformation. So this question takes you through the entire process or the consequences of the unitary transformation that takes us from non-canonical spin orbitals to canonical spin orbitals. Fine. We take yet another question. I just want to announce, if you have any follow-up question on the questions that the problems that we are discussing, please feel free to write in the chat box. We will take them up. All right. Now this particular question talks about the basis set. Remember, after we discussed the Ruthan's idea, we also said that in real life, what are the different types of basis sets that we use, how to identify them, what are their strengths, what are their features, all these things we discussed. And with this question, we'll try to understand some of them. So this question tells which of the following is true for the STO3Z basis of oxygen atom. So if you remember STO3Z, this simply that this is ladder type orbital, where each ladder type orbital is expressed in terms of 3 Gaussian functions. So this is STO3G. And we are talking about for oxygen atom. Option 1 gives that this basis is composed of 3 ladder type orbitals. Now let us try to find out this orbital. Whenever such a question appears, please write down for example, okay, this is for oxygen atom, so this should have been oxygen, but it shouldn't matter. We'll just have 4 electrons. So I have done it for carbon. So now we have 1s2, 2s2, and if it is carbon, it is 2p2. If it is oxygen, it is 2p4. It doesn't matter actually for this particular problem. So you should write down the electronic configuration and then try to write down try to find out how many ladder type orbitals you are going to describe for which atomic orbital. For example, in STO3Z, so this is not a split valence, so this is a minimal basis. So we would use 1 ladder type for each orbital. So for 1s, 1, for 2s, 1, for 2p, also 1. The question said this basis is composed of 3 ladder type orbitals. It may appear that 1, 1, 1, so therefore 3, but that would have been wrong because we know that p orbitals, we just tell them that the p orbitals, but whenever we define a p orbital basis function, we know that it has got 3 Cartesian components, px and py and pz. So therefore there are 3 Slater determinants for the p functions. So therefore total we should have 5 Slater type orbitals for oxygen atom. The second option is this: in the basis only the valence orbitals are expressed in terms of 3 Gaussian functions. Before that we do the expansion. So each STO is expressed in terms of 3 GTOs. That's because this is an STO3Z. If it were split valence, normally in case of split valence, what we would have done is that we would have expressed the valence electrons in a different manner, in the core electrons in the core orbitals, core electrons in a different manner. But in this case, each Slater type orbital is described by 3 Gaussian functions. So therefore, in this basis only the valence orbitals are expressed in terms of 3 Gaussian function. That also is wrong because both valence and core have been expressed in terms of 3 Gaussian function. The contraction scheme of this basis is 6s3p goes to 2s1p in the square bracket. So this square bracket number is for it corresponds to the Slater type orbitals. The round bracket numbers, they corresponding to the GTOs. So let us look at this square bracket first, because we have written down what are the STOs and what are the GTOs. So it says that 2 S type of STOs. I say that that's correct. 1 plus 1, 2 S type of STOs, and 1 P type of STO. This because I see 1 P type. When I say 1 P type, I don't write 3 here because I know when I say 1 P, it automatically means that I have got 3 STOs, but it's a P type. So this is the notation. So this part is correct. Let us look at the GTO part, which is in the round brackets. So it says that I have 6 S type of function, 3 plus 3. So that's correct. There are 6 S type of function, and since already 1 STO is defined by 3 GTOs, so therefore there are 3 P type of GTOs. So this option is correct. The fourth option is that the coefficients and the orbital exponents of the 2s orbitals are same as those of 2p orbitals. If you remember the basis set discussion that we had in the lecture, or you can also look it up in the website that I referred to, you can see that the 2s orbital and 2p orbital, they would have the same orbital exponent, but the coefficients are going to be different. So these questions expect that the coefficients and the orbital exponents are same, but that's not true. Only the orbital exponents are going to be same for 2s and 2p, but the coefficients are going to be different. Okay. We now take up a problem from the time-dependent perturbation theory. So this question reminds us about the two-state system. when the question says when we have a weak and a constant perturbation applied to a two-state system, what happens to the population of the initially empty state? So we know that when our potential energy operator would have explicit dependence on the on time. So in that case, the composition of the two states would keep changing. That means the coefficients would be time dependent, unlike the time independent Hamiltonian. So this tells me that okay, we have two state problem. So therefore, you would immediately identify or recall this relation, which says that what is the population of the second state, which was an empty state at a different time. So it says what are the which are the true statements in this case. It says first it can become 1, that means the population of the initially empty state can become 1 if the two states are degenerate. You remember when the two states are degenerate, that means the omega 2 1 was 0. So in that case, we see that this term becomes the prefactor omega 2 becomes 1 becomes 0. So therefore, the prefactor over here becomes 1. And then I have a sine square theta term, which depends on the strength of the perturbation. So when the two states are degenerate, that means the energy difference between them is 0, we see that the population of the second state, or therefore the population of the first state, they simply change as a sine square function. And we know that sine square function, its upper bound is plus 1. It goes from 0 to 1 because it's sine square. So in that case, we know that population of the second state can easily become 1. Of course, we have to wait for some time. So given that if we can wait for some time, no matter how weak this perturbation V is, the population of the second state or the initial state can become 1. There is all the chances. So this is correct. The second says it can never become 1 if the two states are degenerate. That is not correct because we know that it goes from 1 to 0. So because the two states are degenerate, so they are loosely bound states. So that means the population transport between them happens very easily. So therefore, the second is wrong. Third option tells us that it can never become 1 if the two states are well separated. Well, if the two states are very well separated, that means omega 2 1 is not 0. In that case, it says that it can never become 1. That means there will not be a complete transfer of the population from the initially occupied state to the initially empty state. But that cannot be generalized, although in most of the cases it is going to be the case. But that you cannot generalize because if you consider a very strong perturbation, in that case, the system can completely go from state 1 to state 2. So that's a possibility. The fourth option is the two states are non-degenerate. The maximum value depends only on the strength of the perturbation. If the two states are non-degenerate, then there are two quantities in this. One is the energy difference between the two states, and the second is the strength of the perturbation. So the population of the final state will depend on both the cases. We can have weak perturbation and very close lying state, or weak perturbation with very far away state, or very close lying state but strong perturbation. So both these quantities, that is the strength of the perturbation as well as the separation between the energy separation between these two states, will contribute to the population of the second state. All right. Now, let us take up the next question. It says that in which of the following emissions, the rate of stimulated emission will be the highest as compared to the rate of spontaneous emission. So we looked, when we were discussing this Einstein's coefficient, we saw that the absorption can have, we have the, for the emission process, we can either have stimulated or spontaneous emission. For the absorption, we always have to have the so-called stimulated absorption. So this the coefficients B are for the we have three Einstein coefficients A and B. So we know how the two B coefficients are equal, and the spontaneous and the stimulated emission A and B FIs, they are related to each other by this relation. We derived this relation using Boltzmann's relation as well as Planck's relation for the spectral density. So this question tells in which of the following four emissions the rate of stimulated emissions will be greater, the highest compared to the spontaneous emission. Now what you see here in this case, the spontaneous emission, and this is B is my stimulated emission. So while these quantities are constant, it depends on this transition frequency, the value of the transition frequency. When the transition frequency is very high, then we see that the spontaneous emission becomes stronger. So therefore the stimulated emission will be relatively weaker. Now since the question asks where the stimulated emission will be highest, so therefore we have to find out of these four emissions which corresponds to the lowest energy or the lowest frequency. So you see that all these four quantities are given in four different energy units. So you have to convert them to one any one of these energy units so that you can compare them one to one. For example, this is 3 electron volt, and the second option 23 kcal per mole, which is nearly about 1 electron volt energy. 300 nanometer corresponds to about 4 electron volt, whereas 3000 wave numbers is much less than 1 electron volt, because 1 electron volt is roughly 8000 wave numbers. So this is close to, let's say, between 30%, 0.3 to 0.4 during that range of electron volt. So therefore, if you compare all this, so 3 electron volt, roughly 1 electron volt, about more than 4 electron volt, and this is about 0.3 or 0.4 electron volt. So therefore, this emission corresponds to the lowest energy, and therefore the rate of stimulated emission will be the highest for this emission. Okay, so these are some representative questions I selected from the assignment based on your queries that I received from the class. Okay, so let's see whether we have any more question. If you have any final questions or comments, or any suggestion how to improve the course, or have some other features in this course included, so please let me know. And not only in the live session, you are also always welcome to contact us in the discussion forum, or also by email. If you have any doubts, we'll always be happy to address them. All right. Technodroid says, sir, please make proper playlist of your videos in YouTube. I guess the YouTube videos are yet not available. So once when they are available in YouTube, so of course our technical team will make sure that they are properly arranged. Thank you for that question. Right here. All right, so I do not see any more questions. So thank you for watching, and I hope you enjoyed the course. And let us know your thoughts about this course. Maybe we can close the session now. Thank you very much.